we're going to do here now is reiterate that same concept, right? Just describing it in different ways. And now we're going to talk very, very slowly, piece by piece, on how we establish that. How do we actually facilitate that, taking this one, baby step at a time? So let's think about the initial process. We have fluid moving from the proximal convoluted tubule down into the loop of Henle. We start off with the tubular fluid having an osmolarity of 300 milliosmoles. As we can see, the entire spectrum of that fluid is at the same osmolarity. It's also isoosmotic with respect to the interstitial fluid osmolarity. So the tubular osmolarity and the interstitial fluid osmolarity are the same. The first step is that we can actively transport our ions, our solutes across the ascending limb of the loop of Henle, which begins to increase the osmolarity of that interstitial fluid. So that is the first step. We're moving solutes across the ascending limb through those co-transport mechanisms. Let me pause here. I see a question. A question here. So the fluid stays the same, but the osmolarity is changing. The fluid stays the same in terms of the fluid is remaining in the tubule, but solids are moving, right? Water is moving at first, solids are moving in the ascending limb, so the osmolarity is changing. The makeup of that fluid is changing. Is it more salty? Is it more concentrated with solutes? Is it more watery? Is it more concentrated with water? So fluid is staying the same, osmolarity is changing, okay? Because the various components are moving from that fluid. And that's kind of what we're describing here as well. So first step, solutes move. Second step, we now create a gradient for water to move. Because the solids moved at first, they increased the osmolarity of the interstitial fluid. It went from 300, so interstitial fluid osmolarity 300 here, now 400 here because of the solid movement in this first step. And now we have a gradient for water movement. So because we have a higher osmolarity here at 400 than the tubular fluid, now water can move on the descending limb, which is step 2. Step 3 is that we're going to equalize. So now we're going to reestablish an isoosmotic state in the tubular fluid as more of that fluid gets pushed down into the tubular space, into the loop of Henle. All right. Next, we're going to see the same mechanism kind of repeat itself. Now we have tubular fluid, which has an osmolarity of about 400 initially. We're going to move solutes into the interstitial fluid, which decreases that osmolarity to about 200 as we go up into the ascending limb of the loop of Henle. And what we're doing now is we're increasing the osmolarity of the interstitial fluid, the medullary interstitial fluid, which is the space surrounding the tubule. So as we move those solutes once again, we're going to see that our interstitial fluid is going to go up, right? Our interstitial fluid osmolarity goes up, which recreates a gradient for the movement of water on the descending limb. So now water moves because we have a higher concentration in the middle here, the interstitial fluid, and a lower concentration of the fluid that's coming down the descending limb of the tubule. And because the descending limb is permeable to water only, that water simply moves because of the gradient by osmosis. And that continues to happen again and again and again. We move more solutes, create a gradient, move more water, move more of that fluid down the loop of Henle, reestablish an isoosmotic state, which is what we see here. And then again, we move more solutes, move more water, again and again, until we end up in a steady state. In the steady state, we're going to see a gradient of the tubular fluid going from 300 down to 1400, getting very, very hyperosmolar in the dip of the loop of Henle, and then a gradient going in the reverse direction, going back to our distal convoluted tubule, where we now have an even lower osmolarity of the tubular fluid. That's one part of the equation. The other thing that we have set up by the time we get to steady state is the gradient of the interstitial fluid. It's going to go from 300 up here in the cortex, and as we dip down into the medulla, the deeper parts of the interstitial fluid, we're going to find that that is higher at about 14. So we've just kind of just described how we ended up with that medullary osmotic gradient because of the countercurrent multiplier, right? The movement of sodium and solutes on the ascending limb versus water only on the descending. Okay, let me pause here, see what questions we have. Any questions come up from that? Any additional questions? All right. Now, urea is also playing a big part in creating that gradient. Urea is going to be also uh, reabsorbed across that interstitial fluid and moved into the capillaries because of several urea transporters. We have urea transporter A, urea transporter B, that are helping to facilitate, also urea transport C, that are helping to facilitate the movement of urea from the tubule and reabsorbing it back into the blood. So urea is going to be made by the liver. It's a way for us to eliminate nitrogen, which is kind of the main component of urea. And then it is extremely water soluble, so it can be moved across the tubule along with water, and it's going to be moved according to these various urea transporters A, B, and C. Now, in terms of its being, its filtration, it happens through um, the filtrate. So the filtrate that is in the proximal part of the convoluted tubule is where we're going to see most of that urea being absorbed. So that is essentially happening through the urea transporter C. About 40% of that is going to help create the osmolarity gradient, right? So that is happening early in the tubule, whereas the rest of that, the remaining urea, is reabsorbed according to the collecting duct, which is urea transporter A, and then facilitated through the transporters on the capillaries, urea transporter B. So most of that happening in the proximal tubule, and then we're going to see the rest of that happening across the collecting duct, and then eventually the vasa recta, or the capillary surrounding the loop of Henle. All right. So while we are here, let's kind of introduce this idea of the vasa recta. We're going to talk about its importance in reabsorption. So as we've been speaking about water being reabsorbed, solids being reabsorbed, this reabsorption of important nutrients, glucose, we've been talking about how they are reabsorbed across the tubular space and into the capillaries. But as we get down into the medulla, there's a specific structure created by the capillaries here that's called the vasa recta. So these are much smaller capillaries that are tightly entwined or intimately connected with the loop of Henle, the ascending and descending limb of the loop of Henle. And they're in the reverse orientation. So the arterial side of that is in association with the ascending limb of the loop of Henle. The venous side of that vasa recta is in association with the descending limb of the loop of Henle. That is to say that the reabsorption that is happening on the ascending limb, which is essentially solutes, is facilitated by the arteriolar side of the vasa recta, and the reabsorption happening on the descending limb, again, primarily water, is facilitated by the venous side of our vasa recta, which goes back to the efferent arteriole. Great. Let's think about again, the role of the vasa recta here. So the anatomical arrangement of the vasa recta allows the movement of solutes and water in the opposite direction. And it pretty much prevents the dissipation of our gradient. It prevents the loss of the gradient that we just described, how we worked so hard to create that gradient. And the vasa recta helps us to maintain that solute and water gradient and help to keep our medullary osmotic gradient. So here's our blood flow. And so think about this in the opposite orientation. So our blood is flowing into the proximal part of our vasa recta. So this is from the standpoint of the capillary, not the standpoint of the peritubule or the tubules. This is blood flow coming in the capillary here, starting with an osmolarity in the descending part of that vasa recta at 300 milliosmoles. And as it descends, water is pretty much leaving the ascending limb of the loop of Henle and moving into the descending limb of the vasa recta. Okay, and this is happening by osmosis. So water is moving into this region because of the movement out of the descending limb of the loop of Henle. And the opposite is true. In terms of the ascending limb of the vasa recta, we have an osmolarity ending up at 325 milliosmoles. And this is where we're seeing water moving into the plasma and solids moving into the interstitial fluid. So the osmolarity here is higher because we don't have any of those urea transporters. Remember, the urea transporters, if I go back here, are going to be on our descending limb of the vasa recta only. So definitely think about how the orientation of the vasa recta is kind of in reverse of what we see with the tubules. So our descending limb of the vasa recta has our urea transporters. Our ascending limb has none. So that results in a higher osmolarity because we don't have the ability to transport urea. We talk about how urea is important in creating that gradient as well. All right. So just to kind of recap what we've said so far about the reabsorption kind of overall, kind of zooming out, 70% happens in the proximal convoluted tubule. This is unregulated. 20% happens in the distal tubule. This is including what is happening in the descending limb of the loop of Henle, as well as what is happening under the influence of antidiuretic hormone. And this is all considered about 20% also, when we think about that reabsorption in the loop of Henle. And then about 10% happens also regulated under the influence of ADH as well. This is later in the tubule along the collecting duct. So this is the kind of the big take-home message is that water is being reabsorbed at different parts of the tubule, most of it in the proximal tubule, unregulated, and then through the mechanisms that we just described to establish the medullary osmotic gradient. We also see some of that being reabsorbed in the descending limb of the loop of Henle, and then through hormones also happening in the collecting duct. Okay. Let's go ahead and stop here for today. We'll talk about the role of ADH, the aquaporin channels, and how they can facilitate the regulated reabsorption of water in the collecting